Hello, my name is Rafael, and I'm going to be presenting our work on active learning of conditional B embeddings via Bayesian optimization. In this work, the main problem we are trying to address is the optimization of a function over what we call a state space. We consider that we cannot act directly on the state, but only indirectly via what we call control variables. And as a result, we are looking for the control setting which maximizes the conditional expectation of the objective function over the states. This sort of general formulation shows up in several applications, such as approximate inference, reinforcement learning, and robust optimization. In essence, what we mean by control is the set of variables that you can control in your problem, and the state are only the variables which you can act indirectly upon, but which in a way influence your objective function. In this setup, the major restrictions we are considering are that both the objective function and the state distributions are unknown and or expensive to evaluate. We can only perform a limited number of queries to the objective function via controls which are free to choose, but we only observe a noisy evaluation of the objective function at the resulting state. Okay, so how do we solve this black box optimization problem? If we're taking a Bayesian optimization approach, we need to learn a model for the objective function, and in our case, also learn a model for the state distribution, which is unknown. We use this model to make predictions and use the uncertainty as well to select queries to the objective function. And then we update the model with data on the evaluation and then repeat the process. So to make this work, we need a few regularity assumptions. In our paper, the main regularity assumption we make is that the objective function is a member of a reproducing kernel Hilbert space, which is associated with a given kernel. By that, we mean that f lives in a Hilbert space where you have a feature map that takes points from the input space, which is in our case the state space, and maps these points to features in the Hilbert space. These feature vectors, if you take the inner product of them with any other vector in the Hilbert space, which includes our function, the inner product results in the evaluation of that function at the given point that the feature map is mapping. Similarly, if you take two inputs and pick their feature maps, and then we make the inner product between these two features, you get the kernel between the inputs that are represented by these features. Now, if instead of individual points you have a distribution over states, which in our case is the conditional distribution of states given control, you can also map the distribution to the Hilbert space. And the element that corresponds to the distribution in the Hilbert space is what we call the conditional mean embedding. This element is so-called a mean embedding because if we take its inner product with a function in the Hilbert space, we recover the conditional expectation of that function with respect to the distribution, the state distribution in this case. So what are the issues that we need to address in the paper? Well, first of all, the queries, they are being selected based on past observations. So that makes the data that goes into the models not independent and identically distributed. And the main problem with that is that the approximation bounds that you find for conditional mean embeddings in the literature, they are usually based on IID data assumptions. So any uncertainty estimate that we could get with the current theoretical results would be invalid in our setting that we're making an active learning approach. So in the paper, the main contributions we're making is that we're providing a concentration bound for the conditional mean embeddings estimator under a non-IID data assumption. With this concentration bound, we derive a new Bayesian optimization algorithm that we call conditional B-embeddings upper confidence bound. And we derive also theoretical regret bounds for this algorithm and apply it to optimization problems and also a likelihood-free inference example. The algorithm is based on a upper confidence bound acquisition function, as the name indicates. This upper confidence bound is based on a least squares estimator for the conditional embedding, which is not exactly the commonly found estimator for conditional embeddings defined in the literature, but it's very similar except for a difference in the regularization term. The posterior mean of the Gaussian process over the states over Gaussian process over the state space is what approximates the objective function f in our case, and is part of our upper confidence bound. And we also use the posterior variance of another Gaussian process over the control space, and this posterior variance is what allows us to quantify the uncertainty in the conditional mean embedding estimator. We then embed this upper confidence bound acquisition function into a Bayesian optimization framework, and we get our algorithm. As theoretical results, we provide a confidence bound on the conditional mean embedding, which is based on these GP-like estimates. And if you're familiar with the Gaussian process based upper confidence bound literature, you may recognize an analogy of these results with the traditional GP-UCB bounds. And in fact, our bound is actually based on GP-UCB theoretical results. We derive a regret bound for the CME-UCB, which is a function of the information gain of the Gaussian process on the control space. And that's one of the interesting insights in this paper, that we can quantify our uncertainty on the conditional mean embeddings estimator based on a GP-like estimate. And we also derive regret bounds for another version of the algorithm that's based on a tighter upper confidence bound as well. In the paper, we present also experiments demonstrating the proposed algorithm in the toy optimization problem and application to likelihood-free inference. And these preliminary results show that besides the theoretical guarantees, we can also show that the algorithm is able to perform well in practice. Finally, as future work, we consider applications to reinforcement learning, density estimation, and robust optimization. And we also consider adapting the algorithm to a batch setting, where making queries in parallel with Apache controls. Thank you very much.